Alright guys, the standard that we're going to address on this video today is that we're relating light emission and the movement of electrons to element identification. And so an easier way to say that is how does light being released and the movement of electrons help you identify which element you're working with, and that's what we're going to discuss today. Now, energy travels through space by electromagnetic radiation. Examples of those are microwaves, X-rays, gamma rays, ultraviolet rays, etc. Now, the different forms of electromagnetic radiation exhibit the same type of wave-like behavior that electrons do, and they travel at the speed of light in a vacuum. Now, electromagnetic radiation, this is the spectrum, the electromagnetic spectrum, and this shows you that there are different wavelengths for all of these electromagnetic waves. Now, there's only between this wavelength right here can we actually see visibly with our eye. Okay, all of the other wavelengths greater than it or less than it, we cannot see with our eyes. So this is our visible electromagnetic spectrum. This is how we see the colors. And so different colors operate at different wavelengths. And so if it's a certain wavelength that's blue, if it's another wavelength that's green, if it's another wavelength that's red, and so forth. So each color has its own wavelength. Now, the nature of waves. As you can see, the wavelength goes from one crest of the wave. I am so sorry. The wavelength is measured from a crest of one wave to the crest of another wave, or a trough of one wave to the trough of the next. All right, and so this is the wavelength. Now, as you can see, the red wave has a larger wavelength than the blue wave down here. However, the smaller the wavelength, the higher the frequency. And the frequency is how many times that wave can happen per second. Okay, so the shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. Now, there is a dual wave particle nature of light, and that means that you have a wave, but you also have a photon, which is a packet of energy. That's the dual part. So the light as the wave looks, as you've already seen, the wave pattern, but also there is a light as a stream of photons. This wave is carrying photons, which are little bitty packets of energy. Now, different wavelengths carry different amounts of energy. So the larger the wavelength, the smaller the amount of energy. The smaller the wavelength, the larger amount of energy. So this is a relationship that's opposite from one another. You know, because the larger the wavelength, the smaller the energy. Smaller the wavelength, the larger the energy. Now, atoms can give off light, but they first must receive energy and become excited. So if you have an atom, you have to inject it with energy, which would be giving it a photon, injecting a photon into that atom. And then they also release that energy in form of a photon. So they receive their energy in forms of photons, they also release energy in forms of photons. So if we increase energy into a lithium atom, it becomes excited. Okay, it cannot stay in that state for long. And so once it becomes excited, it has to release or emit a photon. The lithium releases a photon of red light. So that means if you see a spark of red light, that we're working with lithium, the metal lithium. And then it goes back down to its lower energy state once it's able to release that energy. Now, just a couple of things to talk about to understand what just happened. When you have a metal, electrons can actually be released from the surface of that metal when light strikes it. Okay? So in order for the electron to be released from a metal surface, it must be struck, the electron must be struck by a single photon possessing enough energy to break it away. And each metal has a different amount of energy needed to break that electron away. So the minimum energy needed to break that electron away corresponds to the frequency. So if a photon's frequency is below the minimum, then the electron remains bound to the metal surface. And different metals require different minimum frequencies to exhibit the photoelectric effect, or to have their electrons released. Now, electromagnetic radiation is quantized. That just means it consists of photons. Okay, that's all quantized means. So the threshold frequency represents the minimum energy required to remove an electron from a metal surface. So the intensity of a light is a measure of the number of photons present in a given part of that metal beam. So a greater intensity means that more photons are available to release electrons. So the main point of this video is to make sure that you know we can identify elements by light being released. And so if we excite an electron by maybe putting excite an atom by maybe putting fire to it, a metal atom, we can put fire to the metal atom, it gives it tons of energy, it excites it, so then it has to release a photon of energy to get back down to its lower ground state. And when it releases that energy, just like the photon we realized earlier, if it's lithium, it's going to release red. If it's magnesium, it's going to release a different color. If it's calcium, it will release another color. So the color it releases when the photon is emitted helps us identify which element we're working with. All right, so I want you to do a 1, 2, 3 summary today, and I want you to put the most important thing, pick one thing that was the most important thing that we learned today. Then I want you to write 2 questions that we still have, and then I would like you to write 3 words and their definitions that you had not known before this video. And I'll see you in class.